Here we're going to define what an inverse function is. So an inverse function has a property that f inverse of y equals to x whenever f of x is equal to y. So in a sense what we're doing is we're just reversing the direction of the input and the output value. Right? So you see here that the input value y gets sent to x for the inverse function, but the output value of y corresponds with the input value of x for the original function. And an important property about this is the symmetry between the domain and range of our inverse function and the original function. So for instance, the domain of our inverse function is equal to the range of our original function, and the range of our inverse function is equal to the domain of our original function. Right? So one good way to visualize this is that if I have, say, my domain A and my range B, the x values from my domain will get sent to some y value here in my range under the function f. So the inverse function will reverse the direction there so that the input value of y gets sent back to x, and we can see now that the output values here become the input values for the inverse function. Let's look at a simple example. If f of 1 equals to 5, f of 3 equals to 7, and f of 8 equals to negative 10, find f inverse of 7, f inverse of 5, and f inverse of negative 10. And again, here we can visualize with this mapping diagram. 1 gets sent to 5, 3 gets sent to 7, 8 gets sent to negative 10. So to reverse the direction here, we'll get the rules for our inverse functions. So for instance here, f inverse of 7, well, it looks like 7 is being sent to 3, because on our original function 3 was sent to 7, so the inverse will send 7 back to 3. For f inverse of 5, we see that under the original f, 1 gets sent to 5, so 5 gets sent back to 1 under the inverse function. And for the inverse, f inverse of negative 10, we see 8 gets sent to negative 10 under the original function. So the inverse function will send negative 10 back to 8. So here's a fundamental property of inverse functions, that when we do the composition f composed with f inverse, essentially those two operations are going to cancel each other out, leaving us with just the input value x. And that should hold for any value of x that's in the domain of f inverse. Of course, in this case, something that we're allowed to plug into the original, or sorry, into the inverse function. On the other hand, if we do it the other way, f inverse composed with f of x, we see that for any x in A, the domain of the original function, essentially the same thing happens here where those two operations cancel out. And we can kind of visualize this here with the machine model, where I like to picture here that the function f is a machine that takes some input value x and spits out a function value f of x. So if I take that function value and put it into the inverse function, right? So what we're going to have here as the output value would be the original x. In other words, this would be plugging f of x into the inverse function. And we see here it would send it back to the original x that it came from. Right, and this would be the same as if I had the inverse here instead of the original f, and then I had the original f here. Where, okay, if I put an x into this machine, then we're going to get f inverse of x here. And then I put this into the f machine, and then it sends it back to x, where this would actually be f composed with f inverse. Here's the basic process for finding an inverse function. One way to do it is we'll start by replacing the f of x notation with the variable y. And then this gives us something that we can solve for. In this case, we can try and now rewrite our function in terms of x. So I'm going to solve this equation, for x in terms of y. So we're going to solve for the x variable in terms of y. And once we do that, then we have this, this leads to the implicit form of f inverse. In other words, we're representing f inverse as a function of y. But then if we want to express f inverse as a function of x, then we simply just interchange the x and the y variables to get our inverse function. So let's demonstrate this process with this example here. Take f of x equals x cubed plus 2. I'll write this as y equals x cubed plus 2. Now my goal is to just solve for x in the equation. So I'll subtract the 2. And then to get x by itself, I'll take the cube root. And actually here I should wait to change that to x, but here we have the implicit form. So therefore the this is like our f inverse of y. So if I wanted to write f inverse of x, I could write it as the cube root of x minus 2. Now, one thing you can also verify is that property that we saw earlier. That here we want to verify f composed with f inverse equals x. Then we would do f composed with the cube root of x minus 2, which we can then substitute the cube root of x minus 2 in for x here. We see that cubing the cube root cancels the cube root. And then x minus 2 plus 2 just leaves me with x. And similarly, we could also verify that f inverse composed with f equals x as well. So then we're going to be composing the original f, x cubed plus 2, inside the inverse that we found here. So we'll plug x cubed plus 2 in for x in our inverse function. We see here we have x cubed plus 2 minus 2 inside the cube root. Plus 2 minus 2 cancels, leaving me with the cube root of x cubed. And then the cube and the cube root cancel, leaving me with just x. So we see that those two properties here are satisfied with the inverse function that we found. So this is an extra layer, another way of verifying that what we found here is in fact the inverse function. Here's a graphical way to think about the inverse function. We know that on the original f, if it contains the point a, b, then the inverse function will contain the point BA. So if this is a point on F in the original graph, then this would be B comma A would be a point on F inverse. And we see that these 2 points here would be equidistant from some line going right down the middle of our first quadrant there. In fact, this would be the line y equals x. And that symmetry here allows us to then compare the graph of our original function f with the graph of f inverse. We notice here that the graph of the original f compared with the graph of f inverse have the symmetry about the line y equals x. So that'll be useful for helping us understand what's going on when we're comparing the original f with its inverse function.